Good afternoon, fellow Earthlings. I'll take the microphone while I wait for my presentation. So, I'm delighted to be here this afternoon and to talk to you about the topic of my research, which is stellar sounds. Art and science indeed have a lot in common. You've seen it in the previous presentation. And in this presentation, I would like to illustrate how we can use visual arts, sounds, music, and even dance to explain scientific topics. So, to make my point, I'd like to start by taking you on a trip. We are going towards the constellation of Orion, which you might recognize, at a speed of 200 million times the speed of light. And you see that stars are just whizzing by. What you hear are stars, are actual stars, and their sounds are made to be audible to our human ears. So our universe, even though it seems quiet up there, is not as still as you might think, because stars actually ring like giant musical instruments. Next slide, please. I can do that. And in order to make my point about the theory of sound, I would like to use this tuning fork. You hear an A. You hear an A because this tuning fork, as I hit it, starts to vibrate 440 times per second. We say in scientific parlance, it has a frequency of 440 hertz. And as it oscillates, I'll do it again, it vibrates. The vibrations are transferred through the wood in this puppeteer and also through the air to reach your human ears, and you can hear it. And actually all musical instruments are based on this principle of vibration, frequencies, and sound. And depending on the way the instrument is built, for example, the kind of wood is used, or for example, it could be a trumpet, so it's metal, small or big, you will have a different sound characteristic for the instrument. And as you know, bigger instruments give rise to sounds with a much lower pitch, such as a double bass, whereas a violin has a very high pitch. Now, stars, which are huge spheres of gas which produce their own energy by nuclear fusion in their center, they can be seen as giant three-dimensional musical instruments. And they can be unstable in different stages of their life. And such as the analogy for the musical instruments, if you have a big star with a lower density, it will produce a pitch for the star that is lower. And a star that is very dense, a star that is smaller, will produce a pitch that is higher. So stars, just like human beings, they come in varieties. You have big stars, small stars, they come in different colors, and they also come in different ages. And many of these stars, in their lifetime, they will show these vibrations that make the star become a musical instrument. So if you look at the night sky, you could say that you have a whole orchestra of stars up there. And stars with similar characteristics will produce similar sounds. So you could have the violins, the cello, the double basses, the trumpets, all in stars. So this field of research, studying the sounds or the vibrations of stars, is seismology of stars. It's called asteroseismology. And so we are trying to analyze the music of the stars, the sound of the stars, in order to figure out how the instrument, the star, is actually built. What is the material? What is its density? What is the interior of the star? So, do we go out with a giant ear and and pointed up at the sky to receive the sounds of the stars? Well, actually we can't. Because as I explained before, with the tuning fork, sound needs a medium to be transported. And most of the universe is very, very empty space. So the sound cannot be transported from the stars to our Earth. And moreover, our human hearing is very limited. This tuning fork, we can hear 440 vibrations per second. We can hear vibrations between 30 per second and about 1,800 per second. It depends on the state of your ears. If you've been to many rock concerts, it might be a bit lower, but that's the general range of our limited human hearing. Now, sounds that have a higher pitch, so higher frequencies, are called ultrasound for us, but some smaller creatures, higher pitch, might hear it, whereas sounds that are slower, lower pitch, we cannot detect, but bigger creatures such as elephants or whales can hear it. And now the stars are very, very infrasound, because the stars are much bigger than us. So these are very infrasound, so we cannot hear them with our human ears. So we can't go out with a big ear to listen to the stars, but what we can do is actually find out about these vibrations through another medium. Because as these stars resonate with the sound waves, they actually become smaller and bigger. They contract and they expand, contract, expand, periodically, just as the tuning fork goes back and forth 440 times per second. So, and as they contract and expand, they get brighter and fainter, because they get hotter and they get cooler. And this variation of their light output is something that we can detect with our telescopes. So we go out and we look at a star for a certain amount of time, and we see its brightness get fainter and brighter, periodically. And that's what we call a light curve. We do this from the ground with our telescopes and detectors, or from space. We use satellites launched by NASA or ESA to look at the variations of these pulsating stars. So, because these stellar sounds are very infrasound, too low pitch for our ears, what we do when we detect these light variations, they correspond to the sounds in the stars, so we get the frequencies or the pitch of the star. This pitch is too low, but then we multiply it by a huge factor so that it gets into the range of our audible range, our human hearing range. So often this is a factor of about 1 million or several tens of thousands. And if we speed up the sounds of the stars like that, we can actually listen to the stars. And I'd like you to listen to this very nice island of stars. This is what we call a globular cluster. It's a very high concentration of about 100,000 stars. And now look at the image. You see the stars twinkling, right? You see some stars blinking. Not all of them, but many of them actually blink. This video is a time-lapse image of the globular cluster. It is sped up by a factor of about 40,000. So this blink of one star, which takes 1 second in the image, actually takes half a day. So in half a day, the star contracts and expands, gets brighter and dimmer. And at the same time, this contraction and expansion is the sound wave bringing through the star. And you just heard the stars in this cluster. It was sped up by a factor of 4 million so that we could hear it, and it sounds like a whole beehive of stars. Now the stars in this cluster are the typical musical instruments that I study for a living. They are called auroral stars, and thanks to these pulsations, we know a lot about the interior structure of these stars. But there are some things that we don't know, because they seem to be vibrating, getting dimmer and brighter very regularly, but for many of them actually they topic that I've been working on for several years. This particular phenomenon that we don't understand is called the Blaschko effect. It's the periodical freaking out of these very regularly pulsating musical stars. And I studied it for my PhD to start with. And in order to illustrate this topic of my research, I made a dance. And I danced it with a few of my colleagues. So here you see me studying one particular star, my colleagues studying their particular star, all pulsating at their own speed. And I've taken a very harmonious piece of music by Bach, because they are really very regular generally. But then, so the light curve does all kinds of weird things. Which makes our head spin. So they keep on pulsating, and this weird freaking out effect also returns. So these are all astronomers. I actually didn't have to ask for a long time. They were all game for doing this, and then they returned back to their normal behavior. We had one repetition for the dance, and we did it. But since they're all astroseismologists, they're all acquainted with this thing, and they just did their own. So that's it. Thank you very much.